Welcome to Lecture 10, Divisibility, Section 2.3 of the text Elements of Modern Algebra by Gilbert and Gilbert. This is Dr. Gilbert, Eyabi. Section 2.3, Divisibility. Subsection 2.3.1, Well Ordering Theorem. Before I state this theorem, let me go ahead and give us background. In lecture 9, we proved that the number 1 is the least positive integer. Now, what happens if I take a subset of Zipless, a subset which is made up of elements from the set of positive integers? Is it necessarily the case that that subset must have a least element of its own? The Well Ordering Theorem states that if S is a non-empty subset of positive integers, then S contains a least element. i.e., there exists an element M in S that is less than or equal to all the other elements in S. M is the least element. Usually, I don't like to draw pictures when I'm proving, so that if I ask you to present a proof, I don't want you to draw pictures and tell me that is the proof. But I'm going to draw some pictures here just to give you an idea of the proof because it is a little abstract. Now, this is the set of positive integers. The least element is 1. And it goes right up to infinity. There are infinitely many of them. Take a subset S of the set of positive integers. If the element 1 is included in S, then since S is a subset of Zipless and the number 1 is the least positive integer, then obviously S has a least element, and that least element is, you got it right, 1. So if 1 is in S, then 1 is the least element. So the first case is very straightforward. Now let's look at the second case. I pick a subset of Zipless S that does not contain 1. I want to prove that there is an element in S that is the least element. So what is the proof strategy? I kind of forget about S for a while and define a new set L, where L is the set of all elements that are strictly less than the elements that are in S. So if S had elements, for example, 5, 6, 7, and whatever, then L would have elements from 1 up to 4. 1 is the least element in Zipless, and if L is the set of all elements less than S, 1 has to be in L. Observe that the intersection between L and S has to be an empty set. What is our goal? Our goal would be to prove that there exists an element in L, which I'm going to call P0 or P0, such that P0 plus 1 is not in L. And if P0 plus 1 is not in L, then P0 plus 1 would have to be in S, and that would be the least element in S. As a matter of fact, in this my little diagram that I have here, my P0 plus 1 would be 5. And clearly you can see that 5 would be the least element in S. Now I'm going to go ahead and present the proof to you, and it's going to be a little abstract, but just remember that I'm going to be dealing with two cases. Case 1, the number 1 is in S. Case 2, the number 1 is not in S. Before I go into the abstract nature of this proof, observe that if there is no P0 such that P0 plus 1 is not in L, then what we are simply saying is that since 1 is in L, for every P plus 1 would have to be in L. that simply makes L the set of positive integers because it becomes an inductive set, and the smallest inductive set is Z plus. But if L equals Z plus, what does that say about S? S has to be empty because L and S, there is no element in their intersection. So if L only is Z plus, that means S has to be an empty set, which automatically contradicts our assumption that S cannot be empty. So that would force P0 plus 1 to be in S. And that would be the element we're looking for, the least element in S. So keep this diagram here. You can come back to it and look at it. But I'm going to go ahead and present the abstract proof to you at this time. Let S be a non-empty set, very important. And let S be a subset of Z plus, a subset of the set of positive integers. Case 1, the number 1 is in S. If 1 is in S, that means 1 is less than or equal to every element in S because 1 is the least positive integer. In that case, my m equals 1 is the least element I'm looking for. And that satisfies case 1. S has a least element, and the element is the number 1, and we're done. Again, you can go back to lecture 9, section 2.2, and see the proof that 1 is the least positive integer. Case 2, which is very exciting. The number 1 is not an element in S. So what do? We define a set L to be the set of all positive integers P such that P is strictly less than X for every X in S. Just like I mentioned here, that is my S. L, there is no element in common between L and S. So if I define L to be the set of all positive integers P such that P is less than X for every X in S, then we can see that L intersection S is an empty set. Now, the element 1 is in L because 1 is the least positive integer. So obviously it is less than all the elements in S. Again, 1 is not in S. So 1 cannot be equal to any element in S. It is strictly less than every element in S, and therefore it belongs to L. Claim there exists an element P0 in L such that P0 plus 1 is not in L. Again, let's go to our little diagram. There exists an element P0 in L such that P0 plus 1 is not in L. And we shall show actually that P0 plus 1 is in S. Suppose, on the contrary, there is no such P0 in L such that P0 plus 1 is not in L. Then what we are saying is that for every P in L, P plus 1 must also belong to L. But 1 is in L. For every P in L, P plus 1 is in L. That means L is an inductive set. From lecture 9, this would simply mean that L equals Z plus. But if this happens, then our set S is an empty set, which directly contradicts the fact that S is not empty. We have arrived at a contradiction, and this contradiction arises because we did assume that we do not have any P0 in L such that P0 plus 1 is not an element in L. Therefore, we conclude that indeed there is an element P0 in L such that P0 plus 1 is not in L. That is interesting. P0 is from L. That means P0 is strictly less than X for every X in S. Therefore, P0 plus 1 is less than or equal to X. Remember, we're dealing with positive integers here for every X in S. Now, let's investigate both cases. P0 plus 1 could either be less than X or it could be equal to X. Suppose P0 plus 1 less than X was true all the time. What would that mean? That would mean that P0 plus 1 is actually an element in L, and we just proved above that P0 plus 1 is not an element in L. So, P0 plus 1 is not always less than X. Hey, wait a minute. What am I trying to say? What I'm saying is that there exists an X in S such that P0 plus 1 actually equals X. Right here. Set my M to be P0 plus 1, then M is the least positive integer in S, and that proves the Well Ordering Theorem. Very simple proof, nice theorem, and very important. I expect every abstract algebra student to be able to articulate this proof. Subsection 2.3.2 definition: a divisor or a multiple. This is a definition you probably have seen before in a class like discrete mathematics, or actually earlier, even in middle school and high school, but I'm not sure if you did define this concept this rigorously. We say that A divides B with this notation if and only if there exists an integer k such that B equals A times k. For example, 5 divides 30 because I can write 30 as 5 times k. In this case, my k is 6. If A does not divide B, then we use this notation. For example, 3 does not divide 10 because I cannot find an integer k such that 10 equals 3k. I'm going to go ahead and go through a few problems with you on divisibility. Problem number 1. Let A, B, C, and D be integers such that A divides B and C divides D. Prove that A times C divides B times D. The whole idea of giving you this example is to show you how we articulate proofs under divisibility. Now, I'm told that A divides B and C divides D. So, proof. Suppose A divides B and C divides D. Required to prove A times C divides B times D, i.e., I want to prove that there exists an integer k such that B times D equals AC k. But A divides B, what does that mean? There exists an integer k1 such that B equals A k1. Call that equation 1. C divides D. That means there exists an integer k2 such that D equals CK2, and call that equation 2. Remember, I want to prove that BD equals ACK. I have equations 1 and 2 before me. Multiply equation 1 by equation 2, and we have B times D equals AK1 times CK2. And since A and C, K1, K2 are all integers where there is commutativity and there is associativity, this leads to AC times K1, K2, which equals AC times K wiggle, where my K wiggle is K1 times K2, and that is an integer because the product of two integers is an integer. So effectively, I just proved that AC divides BD, and we're done. Problem number 2. Let A be an integer. Prove that 2 divides A times A plus 1. In other words, prove that the product of 2 consecutive integers is even. Remember, A times A plus 1. These are 2 consecutive integers. And if 2 divides A times A plus 1, that simply means A times A plus 1 equals 2K, i.e. the product of 2 consecutive integers is even. As a matter of fact, I want you to try proving that 3 divides A times A plus 1 times A plus 2. And while you are at it, prove that 4 divides A times A plus 1 times A plus 2 times A plus 3. Beautiful concept. I'm going to give you the hint. It's a beautiful concept, very easy to prove. So I'm going to leave it as an exercise for serious students. But let me give you hints. Case 1. Take the case when A is odd. If A is odd, then A equals 2k1 plus 1 for some integer k1. Now multiply A times A plus 1 and observe that it would give you 2k for some integer k. In other words, A is 2k1 plus 1. A plus 1 will just be 2k1 plus 1 plus 1. You already see 2 coming out. And then prove that all of these nicely put together would lead you to some 2k. Case 2. Take the case when A is even, i.e. A equals 2k2, where k2 is an integer. Do the same thing as with the case when A is odd and show that A times A plus 1 equals 2k. Then you can conclude from case 1 and case 2 that if A is an integer, then 2 divides A times A plus 1. And this proof is exhaustive because the set of positive integers can be divided exhaustively as odd numbers, even numbers. Problem number 3. I added problem number 3 because it has a very classic technique that you would need in abstract algebra in so many topics. Let A be an integer and at the same time A is odd. Prove that 8 divides A squared minus 1. Again, even if you haven't seen a problem on divisibility before and it is presented to you, always ask yourself what is required to prove. We want to prove that A squared minus 1 equals 8k, where k is an integer. What is given? We are told that A is odd. So A odd implies that there exists an integer k1 such that A equals 2k1 plus 1. All I have to do is plug in 2k1 plus 1 in the place of A, square it, subtract 1, and figure out how I can write my result as 8 times some integer k. Now, if A is odd, then A equals 2k1 plus 1, where k1 is an integer. So, A squared minus 1, I substitute my 2k1 plus 1. That gives me 2k1 plus 1 all squared minus 1. And I expand that to have 4k1 squared plus 4k1 plus 1 minus 1. And that gives me 4k1 squared plus 4k1. And I can factorize out my 4, and I'm left with k1 squared plus k1. Beautiful. But what do I really need? I need an 8. I need 8 times some integer k. What I have right now is 4. How do I change the 4 to an 8? This is what I meant when I said we are going to visit a classic technique in abstract algebra. Whenever you have k1 squared plus k1, factorize out k1 and observe that what you have is k1 times k1 plus 1. This product right here is the product of consecutive integers. Whenever you have an integer times the integer plus 1, we have consecutive integers. And by problem number 2, the product of two consecutive integers is, you got it right, even. So k1 times k1 plus 1 equals some 2k by problem number 2. You can see the 8 coming out. 4 times 2k is 8k. What does that mean? It means 8 divides a squared minus 1 and we're done. This is a classic move in abstract algebra. Whenever you're given a squared plus a, always view it as a times a plus 1, which is the product of two consecutive integers, and that equals 2k. Beautiful. Problem number 4. Prove by the principle of mathematical induction, which we saw in lecture 9, section 2.2, that 6 is a factor of n cubed minus n for every positive integer n. In other words, prove that 6 divides n cubed minus n for every n in Zipless, and use the principle of mathematical induction. I would leave this as a simple exercise for serious students. Subsection 2.3.3, a theorem, divisors of 1. The only divisors of 1 are 1 and negative 1. Of course, you must have seen this right from elementary school, but this is abstract algebra, and we expect you to be able to prove that if an integer a divides the number 1, then a has to be plus or minus 1 and nothing else. Proof. Suppose the integer a divides 1. Then by our definition of divisibility, there exists an integer c such that 1 equals a times c. Most students will get here very easily, and then they would start saying, well, if a times c equals 1, then that means a has to be 1, c has to be 1, or a has to be negative 1, c has to be negative 1, and they say that's the proof. No, this is a classic proof, and I expect you to be able to remember this and to be able to replicate this proof when needed. Observe that a cannot be 0. If a is 0, then if I multiply a times c, I cannot get 1. So a cannot be 0. That means a has only two options. A can be in Zipless or negative a can be in Zipless. Let me pause here and say that there are several ways to partition the set of integers. One of the ways to partition zips would be odd and even numbers that will form a partition. Split Zipless as 3 subsets: negative integers, positive integers, and 0. Their union would give us z and their intersection empty. So in this particular case, if the element a is not 0, then since a is an integer, a can be in Zipless, or instead of saying that a is in Z minus, we would instead use negative a in Zipless. Same thing as a is a negative integer. Case 1, a is a positive integer. A is an element in Zipless. Follow the proof very carefully. If a is in Zipless, can c not be in Zipless? Because if c is not in Zipless, if c is negative, I'm going to have a positive number times a negative number, and the properties of positive integers, go back to section 2.1 of the text Elements of Modern Algebra by Gilbert and Gilbert if you need to review the concept or the properties of positive integers. You can go back and review those. If A is positive, C cannot be negative because you cannot have a positive number multiplied by negative number to give you a positive number. If A is in Z plus, then C must also be in Z plus because A times C equals 1 is a positive integer. Properties of Z plus. So what does that mean? Remember that 1, the number 1, is the least positive integer. If A is an integer, C is an integer, and they are all positive integers, then A has to be greater than or equal to 1, and, not or, and C is also greater than or equal to 1. A has two options here. One is A greater than 1 or A equal to 1. What if A is strictly greater than 1? If A is strictly greater than 1, then by properties of positive integers again, since C is a positive integer, I can multiply both sides by C and maintain my inequality sign. That only works with positive integers. So A times C is strictly greater than 1 times C, i.e. AC is greater than C. But what is AC? AC is the number 1. So that means 1 is strictly greater than C. Wait a minute. That contradicts the fact that C has to be greater than or equal to 1. That contradiction arises because we did suppose that A was strictly greater than 1. Therefore, A cannot be greater than 1, and the only thing A is left to be is equal to 1. From case 1, we have shown that if A divides 1, then A has to be equal to 1 as long as A is in Z plus. What happens if A is not in Z plus? Then negative A would have to be in Z plus. Again, check section 2.1, properties of positive integers. By properties of Z plus, since negative A is in Z plus, by properties of positive integers, again section 2.1, negative A times negative C equals A times C, and A times C from the very beginning is 1. Just like in case 1, if negative A is in Z plus and negative A times negative C equals 1, then negative C would have to be in Z plus also. But if negative A is in Z plus, negative C is in Z plus, 1 is the least element in Z plus, that means negative A is greater than or equal to 1, and negative C is greater than or equal to 1. Again, negative A has two options. Negative A can either be greater than 1 or negative A can be equal to 1. So let's suppose that negative A was strictly greater than 1. If negative A is strictly greater than 1, then since negative C is in Z plus, by properties of Z plus, I can multiply both sides by negative C and maintain my inequality sign. Remember, negative C is a positive integer. Let the negative not deceive you. So negative A times negative C would be strictly greater than 1 times negative C. That would mean that negative A times negative C is greater than negative C. But what is negative A times negative C? Negative A times negative C is 1, which means 1 is strictly greater than negative C, and that contradicts the fact that negative C is greater than or equal to 1. This contradiction arises from the assumption that negative A was strictly greater than 1. Therefore, negative A has to be equal to 1. But if negative A equals 1, then negative times negative A, which is A, would be equal to -1. What have I showed? I just proved that if A divides 1, then either A is 1 or A is -1, and that brings us to the end of the proof. Theorem, division algorithm. This is also known as the basic theorem on divisibility. The theorem simply says that if A and B are integers with B greater than 0, then there exist unique integers Q and R such that A equals BQ plus R is bigger than or equal to 0, but it is strictly less than B. There are two things here, existence and uniqueness. Proof. I am going to leave the proof of the basic theorem on divisibility as a simple reading exercise for serious students. So if you would go to page 86 of your text, Elements of Modern Algebra by Gilbert and Gilbert, you would see the full proof. It's not complicated, but I'm going to leave that for you as a simple reading exercise. What you would need to prove is to verify existence and uniqueness. Just as we've done before in proofs involving uniqueness, you would have to suppose that there exist integers Q1, R1, Q2, R2 such that A equals BQ1 plus R1, A equals BQ2 plus R2, and then show that Q1 must be equal to Q2 and R1 must be equal to R2. Again, I would leave that as a simple reading exercise for serious students. Example 1. Let A be the number 357 and B the number 13. Find Q and R such that A equals B times Q plus R, and R has this specification, is bigger than or equal to 0 and strictly less than B. Solution. Simple computation would give you 357 equals 13 times 27 plus 6. All you have to observe is that the remainder R is bigger than or equal to 0 and also strictly less than B, which is 13. That is the case, so we're done. It gets more exciting if A is a negative number. What if A is negative 357 and B is 13? Find integers Q and R such that A equals BQ plus R and R is bigger than or equal to 0, very important, but less than B. Well, from the above, we have that 357 equals 13 times 27 plus 6. Since A is a negative number, I can hit negative all across, and that would give me negative 357. My B has to be positive, so I leave it positive. My negative goes into 27, so that becomes 13 times negative 27 plus negative 6. I would have been done except that my remainder is not bigger than or equal to 0, so more work has to be done. The technique we use here is actually a classic technique. We add and subtract B. In this case, B is 13. So remember that when you have this and your R is not bigger than or equal to 0, add and subtract the number B. If we do that, we would have 13 times negative 27 plus negative 6 plus 13 minus 13. Negative 13 can be written as 13 times negative 1. I have 13 times negative 27 plus 13 times negative 1. Add those together, it will give me 13 times negative 28, and negative 6 plus 13 would give me 7. My 7 is bigger than or equal to 0, and it is less than 13, and this becomes my Q, and this is my R, and I am done. Let A equals negative 921 and B equals 18. Find integers Q and R such that A equals BQ plus R, where R is bigger than or equal to 0 and strictly less than B. Good luck. God bless you. Thank you.